dame el coso. I also noticed that I have to like talk more into the camera. I think I have to sit more this way.
Yeah, especially if you're going to introduce something about neutrons, right?
Hello, hello, hello. What do you think of neutrons all day?
Yeah, pretty much.
Because neutrons is a topic for like a month.
You're telling me.
That's a big topic. And I don't even know all the details, all the observations that scientists or technologists, whatever you call them, all the observations they made, I'm not aware of.
Like, oh yeah, you gotta.
I don't know what properties neutrons have or where they come from or anything.
Hello, everyone. Here discussing neutrons with my son on the other side.
Hi, guys.
And no, you should show your face. Really, you should come around, show your face at least once. Yeah. Anyways, we started with the neutron this week. And I started out with this. I started out by sending, I've got it too big. Let's see if I can make that a little smaller. Something like this. There we go. We started with this, just a kind of summary of how the rope model handles the neutron. And we started with the atom on the left-hand side, always the hydrogen atom. We want to go really slowly. We want to go easy on us, on ourselves. So we start with the hydrogen atom there. And the neutron is on the right-hand side. And you might ask, if you're never seen this, you might say, well, what are you referring to? Well, the atom is made from every rope that comes from the universe. One thread goes left, the other one straight ahead. The one that goes straight ahead forms the proton, which is that little blue dot in the center, and the one that went around, we'll call that the magnetic thread, the red one there, that one forms the electron shell.
Do we have a shorthand word for this, like the thread atom or the rope atom?
Well, I call the electric thread the one that's going to make the proton.
No, I mean a word for the model itself. The thread atom or the rope
I call it the rope model of the atom. Yeah, the rope model of the atom. Anyways, if every rope in the universe converges upon our hydrogen atom, all those ropes crisscross in gazillions of places in the universe, in space. And what does that mean? It means that, okay, what do we call those crisscrossings? What do we call those convergence of ropes? Well, that's what we're going to call a neutron. There you see it. You'll see the difference between a proton and neutron on the lower left-hand side. And here's a better picture of it, a comparison of the hydrogen atom against the neutron. The hydrogen atom essentially is, convergence of ropes up to the electron shell, which is that red circle there on the left. And what continues are those blue straight lines, which are going to be the electric threads.
Just to clarify, the colors are
arbitrary.
They're all the same color.
Not only the same,
they're all the same thread.
There's a single thread in the entire universe.
The color coding is just so that we can understand it better.
Right. So the blue thread of the rope goes straight and forms the proton, and the red thread, which we'll call the magnetic thread, just to be in line with convention, goes around and forms the electron shell. So it weaves the electron shell. And that's our atom. What is the neutron? The neutron's the guy on the right. And that's simply convergence of ropes. As you can see, there's no forking out of the electron of the magnetic thread, both electric and magnetic thread, at the distance from the center as you see on the left-hand side. So the ropes just continue. That's a convergence of ropes, and that's what we're going to call our neutron. Okay, so that's our starting point. Where did we get this? Is this out of the blue? I mean, can we also introduce angels and who knows what else? Well, hopefully not. We've got here. Let me get this out of there. We get this from a couple sources. Okay, and here's the first source. As you may be well aware, atoms have different levels known as shells or orbitals. And there you have the 1s, 2s, 2p, and so on down the line, 3s, 3p, and so on. And here is an image of each of these levels, okay? And that's what the researchers have come up with. And we totally agree with this because we're saying those balloons are the are actually not orbitals, but they are actual balloons. An atom is made of balloons. Those balloons are made of the threads that comprises light. That same thread forms these balloons. So we have no problem with this orbital model. We're just saying orbital is a concept, and what we're saying is we're going to replace that concept with an object. We're going to say these are shells like an eggshell. These are balloons like a rubber balloon. These are weaved. These balloons are weaved with the threads. Okay, so that's what we have to explain. So that's one of the issues. But while you look at that, you will notice that, you know, they get bigger and bigger. And the bigger they get, the atoms, the more neutrons they have in them. And so one of the questions that comes up is, why would that be so? And so one of the ways we can visualize it, at least under the rope model, is that the bigger an atom is, the more neutrons we're going to find in there, simply because, you know, the atom is bigger. The size of the atom has grown, okay? So it has a chance of incorporating more neutrons in there. It's just as simple as that. And here's one image of that under the rope model that I try to put out there. Wrong one. Let me get the right one. Where is it? Is it this one? Let's see. No. That'll go next. Okay, so this is the orbital. What am I missing? Yeah, this is the one. No, this is a bigger image. I'll get it. Give me a second here. Oh, this is here it is. So what it is here's an atom, and it gets bigger and bigger and bigger, and by doing so, it incorporates a neutron, which are those green little stars there that you see. And why does it do so? It does so because the atom essentially expands. In other words, the electron shell is what is expanding. The balloon becomes bigger, and there you see a bigger image. In other words, why atoms are, you know, heavier atoms incorporate more neutrons. The electron shell simply expands, or several of them expand, because keep in mind that, you know, these shells are nested inside each other also. And here, this is tritium. Tritium, when it incorporates two neutrons, otherwise it's deuterium. And here you will see once again how the electron shell just gets bigger, incorporates more neutrons. And that's why we have to, that's the justification that the rope model gives for why there are more neutrons in heavier elements, okay? And again, tritium and deuterium also are there, portrayed there. Okay, let's see. Here's how the neutron converts to an atom to a neutron. You have the atom, it's pumping normally. That's the quantum jump there. Now it's going to convert into a neutron. The way it does so, the electron shell compresses or collapses, and rolls itself back onto the proton, in other words, the electric thread that forms the proton, and becomes a neutron. And then the opposite occurs every 15 minutes, and that's when the neutron converts back into an atom. And if you watch it here, you'll see what's happening. Here it's converting back to an atom. Now it's going to pump. And now you'll see how it converts from an atom to a neutron. The thread just rolls back in there, and you have ropes back again, and there's your neutron. The red line around is just to show you where the electron shell was, but the neutron does not have an electron shell. Okay, so you see that? See what's happening there? Mm. The rope simply winds and unwinds itself. And it doesn't tear, it just winds and unwinds itself. That's all it does. Okay, and so that's the model that we propose for what these people observe in the lab. So we have no problem with what they observe in the lab, what they're reporting. We can mimic that with a rope model. We can simulate it. So I don't have a problem with that. As long as we have an explanation. If there's a wall there somewhere that we can't explain, we need to find out in more detail what these people really measured, observed, etc., etc. Remember, they use the word observed. They never observed anything. What they do, they infer. They use the word observed to say that they inferred. And that's quite misleading, because people say, oh, the scientists saw. No, they didn't see anything. They're inferring. They're assuming. Okay, so that's one of the things we have to answer, and that's our answer to that. The other one is the beta decay here. And this is, again, this is just a mathematical depiction of what they believe is happening. You have a carbon-14, it's going to go into beta minus, it's going to turn into a nitrogen-14. How does it do it? One of the protons, one of the neutrons converts into a proton. So we lose a neutron and gain a proton. That's essentially what it is, okay? And they don't explain the process, they just say it is so. And this is the mathematical version of it. This is how we make sense of it. We're saying that carbon-14 had a neutron. Neutron weighs a little more than a proton and an electron, so they added what is called an anti-neutrino, okay? And essentially, you have one less charge, one extra charge. In the case of beta minus, you gain a charge, because now you have a proton. Proton is positively charged, right? And electron is negatively charged. So now you gain a charge, but you lost a neutrality, which is the neutron. What happens in beta plus decay? The opposite. You have maybe carbon-10, it goes into boron-10. And what has happened here? Well, one of the protons and its electron, right? Both of them together become a neutron. They neutralize each other, okay? And it releases in the process a neutrino. So we have the anti-neutrino and neutrino as fudge factors introduced there in the guise of a particle, which is also misleading, because none of these are particles, by the way. This is how they represent them pictorially, but when you put them against the wall, the mathematician will tell you, oh, by the way, a particle is a field, okay? So what you're staring at there is just an equation, which is depicted with a little ball, which is, that's how they do it. Okay, anyways, they do it mathematically. How do we explain it under the rope model? We have to give some kind of physical interpretation for this, assuming that what they're saying is correct, okay? And let's see, that was the beta decay, so I think it's this one. Yeah, okay, so this is how we portray it. No, this is not what I want to show. Beta decay. Where's my beta decay? Oh my God. That's the equation. It should be. I can't find it now. Oh, here it is. Jesus. Okay, and that's the one I showed earlier. In other words, the beta decay is simply a conversion of a neutron into an atom and vice versa. Okay, and so we can explain it. We don't use the math. We don't need to. We're going to show why it doesn't have any charge. It doesn't have any charge because it doesn't have the electron shell expanding and compressing. Okay, that you're seeing there, that's the quantum jump, and we don't have that with the rope model. Once it converts into a neutron, there's a neutron and it has no charge. It's just a bunch of ropes that converge on a center.
Could it be said that the neutron is kind of like an atom that compressed all the way, because we have, or a shell, because the shell's getting bigger, getting smaller,
Yeah.
getting bigger, getting smaller, and a neutron is like if it went all the way small.
The way I look, that's one way of looking at it. That's a good point. I look at it as simply the unrolling and the rolling and the de-rolling of the rope. That's one way of looking. The other one is what Hans just said. What if the electron shell simply collapsed? Remember, the electron shell is pumping there, right? So it does have the possibility or the ability to get closer to the nucleus. And why is there any problem with having that electron shell collapse all the way to the center of the proton? And maybe that's the mechanism. So you can take it either way. One of those two might be happening almost surely if this is what they observed in the lab. If this is the way Mother Nature runs her shop.
This is all assuming what they testified is correct. Let's just take it as an assumption.
Correct.
This is how we could explain it if that is what they actually saw.
Yeah. My point is that we do have, under the rope model, we do have explanations for each one of these observations in the lab, and we do not go into the math because
it's complicated.
No, because we trust the math. The math, no, it really isn't that complicated. It's just
Yes.
No, they just use mass. They say we take the mass of the proton.
Not the math is complicated. I mean the qualitative depiction is complicated.
Oh yeah, the qualitative. But that's why we try to give a physical interpretation to the equations. And that's the physical interpretation. And the final thing we need to, at least, I can't say the final, I'm sure we got to explain a lot more, but here's another feature that we need to explain. It's known as the cosmic microwave background radiation. And it looks something like this. And this is taken from, this is the image finally compiled by WMAP, the Wilkinson anisotropy, whatever. This is they took many readings of the universe, of the visible universe, and they see that there's this cosmic background radiation throughout the universe, which was detected in the 60s by Penzias and Wilson, and what it is that they claim that it's in the microwave range, and it's approximately 3 degrees Kelvin, almost absolute zero, and it just fills space, this radiation. And you might say, well, what does that have to do with a neutron? And I'm saying, yes, it might very well have to do with a neutron because of this. And I'll just show you. First of all, let me put God up there. We need to put poor old God. Because one of the things you got to figure out is, what's this black stuff? And I say that's heaven. It's got to be heaven, because I don't know what could be encapsulating our universe. And we need to identify that black stuff.
Heaven looks dreary.
And, so I put God there, move him around, right? And that means, I guess that's heaven. That's where we're all going to go after we die. Okay, so anyways, the point is that this is why, this is how we explain it, okay? And we explain it this way. We say, look, well, this is first the official version, what the cosmic microwave background radiation is. Electromagnetic radiation is a remnant from an early stage of the universe in Big Bang cosmology. So in order to believe in this, you got to believe in the Big Bang. In other words, the explanation they give. They're saying this is some radiation that is left over from the explosion. If they don't like to call it an explosion, many of them don't. And I think it is an explosion.
Flash? What do they call it?
They try to do a little semantics
what's a
there. They say,
bang?
well, it's not really an explosion, but it is an explosion.
They call it the Big Bang.
Yeah,
a bang is an explosion.
Well, that was I think it was Fred Hoyle who gave it the name of Big Bang, and he was anti Big Bang, so he came up with a Big Bang, and they liked the word and the term, and they used it. Okay, the point is that this is supposed to be radiation that's cooled down after 13.7 billion years. Initially, it was very hot, big explosion, right? And all this radiation over time just kept cooling. Today it's only at 3 degrees Kelvin, almost 0 degrees, absolute 0 degrees, right? And so this is what they're detecting. They're saying it's coming from everywhere in the universe. Okay, I think it's Steve Carruthers who questions that. He says, what they've done is measure it in the vicinity of the Earth, and what they're really measuring is stuff that's around here, not that's out there in the universe. Okay, so there's an issue on that. That's one issue that's brought up. But it says the following. In older literature, the CMB is also variously known as, well, okay, you got another name. And it's a relic radiation, again, because it's a relic from the original Big Bang. The CMB is a faint cosmic background radiation filling all space that is an important source of data on the early universe. That's when God created. So I'm going to leave God down there if you don't mind, because he created this. That's what religious folks say, that all they've done is proven that God does exist. They like the Big Bang, and they like all the proofs that the mathematicians are providing for the existence of God. So they love all that. It says universe because it is the oldest electromagnetic radiation in the universe. So now we have age for this magnetic radiation, dating to the epoch of recombination. With a traditional optical telescope, the space between stars and galaxies, the background, is completely dark. However, a sufficiently sensitive radio telescope shows a faint background noise or glow, almost isotropic, that is, not associated with any star, galaxy, or other object. This glow is strongest in the microwave region of the radio spectrum. So that's essentially the CMB. Okay, that's a description. It's just a relic of the early explosion. And okay, so again, what does this have to do with neutrons? And I'm saying it has to do with neutron in this sense. Here's my version of it. And let's let it take it all the way to the beginning. You're going to see the neutron. First, we're going to build the neutron. Okay, the neutron is a crossroads of ropes. And there we get a blow up of that little neutron. Those neutrons are going to fill space. And all these ropes and all these neutrons are out there. They're just transferring, or better yet, across a neutron, which is a crossroads or convergence of ropes, there's a lot of signals going through there. So a neutron is like the, corner where two highways meet, where two streets meet. You got the lights, all the cars coming in both directions. And so the neutron that's what it does. It just sends signals or relays signals from one atom to another. That's essentially what a neutron does. And of course, that's got to be, when all these ropes crisscross there where the neutron is, we should have some kind of little signal, something we can tap into, something we can detect. And that's the cosmic microwave background radiation. That's the CMB. That's the role of the neutron in the universe. And maybe Mr. Carruthers is right. Maybe since we have more matter in the vicinity of the Earth than we have between two galaxies, for example, maybe the CMB is not found between two galaxies because there's absolutely or very little out there. On the other hand, close to where matter is, maybe we have more neutrons, just like we have more atoms in this region. And so when we send our probes out there, in the vicinity of the solar system, well, we're going to detect neutrons because there's a crossroads of signals there. And I'm sure that's the 3 degrees Kelvin that we're that these people are sensing. That's what it appears to be.
Oh, I'm about to shit on all that.
Oh, okay.
I'm just waiting for my turn to speak.
Okay, you have the floor.
I'm letting you set yourself up.
Let me just give him an introduction here. It turns out that we discussed it last night a little more about the neutron after we adjourned here. And
there was really more questions than discussions.
Of course. We have more questions than answers for sure. One of the issues that came up is how a neutron moves, and maybe that's what Hans is going to address in a minute here. But one of them was, whether a neutron moves, or whether, because one of the issues there is that maybe a neutron moves along a rope. Okay, just think of that, sliding along a rope. And so all the other ropes are stuck to that center, and it's the center that's moving only along one rope in the direction it's moving. And when it moves in another direction, it moves along another rope and carries all the others with it, assuming. We're just assuming this, right? So the question is, hold it, we had a crossroads, and now the neutron moved out of that crossroads and moves on its own, outside of that convergence. And that's one of the issues we wanted to answer there. So yeah, go ahead.
We got the floor. I got a long sentence here. It's not a question; it's a statement that I want you to hear.
Oh, okay.
As you were speaking, I was writing it down, trying to write it precisely. Okay. So here it goes. If neutrons and hydrogen atoms are interchangeable, right?
Yeah.
Neutrons turn into hydrogen atoms, or can.
We are assuming.
And hydrogen atoms can turn into neutrons, we assume. Assuming this is correct.
Yeah.
And you can't have a hydrogen atom without it being connected to all atoms.
Okay.
Then all neutrons are connected to all atoms and neutrons in the universe.
Yes.
So it isn't that every atom in the universe is connected, it's every knot in the universe is connected.
Not being what?
Every proton and neutron. Every proton and neutron is a knot.
Yeah.
And every knot in the universe is connected to every other knot.
Yeah.
So you can't speak of neutrons as being the intersection where ropes cross.
Why not?
Because there are intersections where ropes cross that don't involve all the intersections. The only place that you can have an intersection with all is an atom, is a proton, or a neutron. It's that every atom has to specifically target the neutron. It's not by accident wherever two ropes cross, or three ropes, or four ropes, or as many ropes as you want. It's that they all actually have to target that spot, that knot.
It's that I don't think you're going to get 3 or 4 ropes. You're going to get gazillions of rope no matter what.
Yeah, but you can't get all.
Well,
unless they all aim at it, you can't get all. I drew it. You can't draw.
Okay. Well, so you're saying that there could be, let's assume that's true. The implication there is that perhaps, just perhaps, right? A neutron has a different, in other words, a crossroads of ropes, right? Neutron has different mass in different regions of the universe.
No.
Well, why not? I mean, can't that be the case?
Because then that neutron cannot convert into a hydrogen atom.
Maybe that one doesn't have that property.
That would be different.
Maybe it's got to have a certain density of ropes in order to be able to do that.
Can we call it a neutron, or do we need a different word? Maybe it's a neutrino. We have a fake neutron here because it's not a neutron.
It's something.
Because a neutron moves.
We have to consider, yeah.
It can be held hostage. It's a spot. It's a knot there that kind of it's a stake in the universe. It's a spot that says, I am here. You can't unravel me. While that's different than the happenstance of crossroads, that this fake neutron that cannot turn into a hydrogen atom because it is not connected to every atom in the universe. Just whichever atoms happen to cross there. You could have maybe 50,000 crossings at one spot, which is probably common, but not all. That one can never turn into a hydrogen atom.
Well, there's another couple issues that have to be answered, and that's the motion, the movement of a neutron. And that's a monster.
But now we need a different word.
But hold it. Let me finish what I want to say here. One of the issues that came up yesterday that we had is that Imagine a neutron converting into an atom, just like we showed a minute ago there, okay? Neutron converts into an atom, the atom moves, converts into a neutron, and we can safely say that that neutron, the original one, moved. Okay, keep that in mind. And once again, you know, you have a neutron over here, supposedly across rows of ropes. It converts into an atom, okay? The atom moves. And then over here, after 15 minutes, whatever, it turns into a neutron. And you can safely say that that node over here, that knot over here, is now over there. That's one issue. The other one is that, you know, again, the movement of a neutron is quite spooky, because it's not an easy thing to imagine, assuming it's a crossroads of ropes, right? And assuming that it can convert into an atom and vice versa. Just the neutron being able to move, it's like, you know, the crossroads moves.
No, but I just destroyed that.
Well,
because
okay,
we're talking. No, but then you didn't listen, or you're not hearing me. Because if a neutron can turn into a hydrogen atom, then it has to have a knot. It's a knot there. It's a spot there. If you can't move a crossroads away from there, you can't move a line of if a hydrogen atom over here and a hydrogen atom, yeah, you can't take a rope out of there. So it's not a crossroads per se. That's the wrong word. Crossroads is like 2 ropes or 50,000 ropes. It's not all the ropes. All the ropes is like a specific spot. It's like a singularity. It's a point or a dot, whatever you want to call it, a spot that actually takes rope. It's like it takes every rope hostage in the universe. It's saying, I'm here, everyone has to be connected to me.
Except that there's another possibility. So that's why we have to brainstorm a lot here. But here's another possibility. I'm saying once a neutron is formed, a neutron remains. In other words, you have a crossroads of ropes, right? And now that rope does not come unwound from that center. That center is now permanent. And now, yes, not only can the neutron move, it can convert into a atom back and forth. Are there neutrons of different weight, of different densities of rope? Maybe we have not been able to measure something that accurately to find out if there's a neutron that's missing a rope or whatever.
I don't think there's a such thing as a neutron. You have to give it a different word, because it's not a neutron. As soon as you have a neutron that is not connected to every atom in the universe, it's no longer a neutron. It
is connected to every atom in the universe.
But then you can't have differing weight, mass. It's either connected it's either made. It's made of every atom in the universe.
Of every rope.
Of every rope, yeah. It's like the atom, only with the electron shell crushed in all the way, essentially rewound into the rope of every one. That atom is every neutron has the same weight as every neutron, because once you take one rope away, it's not a neutron. It can't turn into a hydrogen atom anymore.
Why not?
Because you can't have a hydrogen atom without every connection. So you need a different word for that monster, whatever you call that.
Okay, but look at another. We always have possibilities. We have a hydrogen atom, and it's connected to every rope in the universe. Yes.
Connected to every atom.
No, we have the hydrogen atom. It's connected to every rope.
What do you mean?
Every rope in the universe converges upon
our... converges. That's right.
Okay, so it's connected with every rope that connects it to every atom in the universe. This atom converts into a neutron. That means that neutron, at that moment in time, also has every rope in the universe connected to it. Okay? And now it becomes permanent. It doesn't lose any ropes. So now this neutron is no different than an atom in the sense that it also moves around, just like an atom moves around, and then can convert back and forth into an atom or into a neutron. And maybe that's one of the possibilities. Again, a lot of this needs some brainstorming and try to figure out how it matches what these people observed in the lab.
As far as I can tell, that is the only remaining possibility.
Well,
the only
you
other
have brainstormed enough.
Well, that's the best I got. That's the best we've got.
Yeah, I know. It's one of those things we can only propose and
but it's not that far-fetched to talk about atoms, a hydrogen atom that has its electron shell completely collapsed,
Uh-huh.
and there you have a neutral hydrogen atom that still is a spot. In other words, that is connected to every atom in the universe, every other spot.
Yeah.
That's the right way. It's not connected to every atom because it's also connected to every neutron. It's like neutrons are part of the connected to everything family.
Yeah.
That's the weird thing. If it can turn into a hydrogen atom and back, if it's permanent, so to speak,
Yeah.
then it's part of the connected to everything in the universe thing. While you can't really talk about it as a crossroads at that point, because crossroads is more like just happenstance, whatever ropes happen to go by each other. Like if you take two lasers that cross, at some point there was happenstance that you had many ropes going through each other.
But think about one thing. An atom converts to a neutron. We're going to concede that as an assumption, okay? So we'll accept that theory, that explanation. That's what's happening. Okay, fine. So an atom converts into a neutron, and we visualize it originally as, okay, it's a crossroads of ropes. Now, those ropes may not be coming at the same angle at every single point in time, especially if the neutron moves around. So now that a rope that was coming in, let's say at 90 degrees here, right? Suddenly the neutron moves, that's 91 degrees or 89 degrees. Now it's changed that rope. And that would happen with all the ropes. You know, they would all change their direction because suddenly you're moving this thing around. And so again, that's one possibility, but think of it again one more time. In a region where there's lots of matter, such as in our vicinity here, I don't know if there's a different kind of atom and a different kind of neutron out there between two galaxies, between 2 million light years in the middle of nowhere. Are the gases there, the neutrons there, the hydrogen atoms there, are they all the same as what we have here?
Or even weirder, the one that I still haven't been able to get over,
the one at the edge of the universe,
which has a bald spot. It has a bald spot on the outside, right. Whichever edge it's on, it's got a bald spot,
and it's coming all from the inside.
Yeah, so you can have some going up, going right, left, down to the middle, but it's got a bald spot on this side.
Maybe because again,
necessarily.
No, not necessarily. No, hold it. Yeah. Keep in mind that the threads are swung around, and when you swing around the threads, now you have them on all sides, right? Because you could be, depending on what atom we're talking about anyways, but I mean, if the atom is swinging threads all around itself, right? Think of it for a second like that. You could have the magnetic field of the atom on the back side of it, even though there's no atoms coming there. It's just that you swing the thread, and now that thread is coming behind you, and that's a constant flow.
Yeah, but it's still not a sea urchin. It's a bald sea urchin. It's a sea urchin with a bald spot.
Yeah, we would have to draw that one to really visualize what an atom at the edge of the universe would look like, let alone a neutron. So, these things have to be mapped. We have to try to brainstorm, find out, what solutions we give to some of these things. And again, a lot of this has to do with what you concede as, what these people observed in the lab. They've interpreted everything in terms of particles. Now we have to interpret the same thing without being in the lab. We have to just take their word for it and say, well, how would we explain if this is true? If this is what they saw, how would we explain this, or how would we simulate or model it with the rope model?
Or it's kind of like, depending on which assumptions you take on board, you end up with different scenarios. Yeah. Depending on, if you take on assumption A, assuming this is true, then you're going to end up with a different model. If assuming light has this property, it has that property. I mean, light we've kind of got down more than neutrons and gluons. When they go into the weird stuff, it's like, okay, now
well, for sure,
what part of this is particles? True? What part isn't? I had a question about the atom model.
Oh, okay. You atom, we finished that. We've proven that.
Oh man, that's a big one. Is there more thread on the electron shell or in the proton?
I would think that on an electron shell you have more thread because it's got more volume.
Yeah.
But keep in mind that
Isn't the proton heavier?
Huh?
Isn't the proton heavier supposedly? than the electron?
Yes and no.
Oh, okay.
See, because here we're talking
boy.
about what have they accelerated. They think they're accelerating electrons. That means what is that? That's current. And how do we visualize current? Well, nothing is accelerating. Everything is just twirling in place. So, you got to put your mind, what are these people doing? That's why you have to be careful with their interpretations. They interpret everything on the basis of bullets being shot from a gun. And if that's not what's happening, if what we are really, if the way this thing really works in, if we had the eyes of God and we could see it, it's a drill bit twirling in place.
Yeah.
Well, that's different than shooting with a gun, and so
it changes
the outlook completely. And so when they say, "Look, what we've done is we shot an electron,"
it took less to shoot the electron than to move the proton. So they're going, okay, then the electron weighs less. But you're saying the electron, weighs is the wrong word, but it has more thread. There's more thread in an electron shell than a proton, which is weird.
No, not weird, because keep in mind
because you're flipping it on its head. You're saying the elephant weighs less than the feather.
Oh, in that sense, you could say
as we've been taught in school.
Right, but I'm referring to something else. I'm saying that if that's the case, if the electron shell is what, and in fact you probably need to calculate that, because I don't know if that's completely true. Remember, the electric thread is the diameter, right?
Maybe not.
No, but we're assuming that the electric thread is the diameter of the hydrogen atom.
No, because as we talked about the other day, it can curve.
Oh, okay.
It cannot. You don't know how many circles it's making around there in the middle until it goes out.
No.
You don't know if it's always just. On top of the fact that a straight line is by definition shorter than a curved line, isn't it? No. That's not right.
Straight lines, shorter than a curve. From point to point, yeah. The straight line is the shortest path.
But, as a simple question, is the proton a perfect sea urchin in the sense that the thread that comes in goes straight every time? Is it always a straight? Straight lines in there?
All you can do is simulate it both ways.
Or assume and then see what you end up with.
Correct.
Assume.
But let's assume for the sake of argument.
It's logic. It's really logic. Let's put this assumption in, see what we get.
Yeah. And let's assume for a second that we have the electric thread. And let's assume that it's the diameter of the hydrogen atom. We're going to deal with the simplest atom. We've got enough headaches with that, okay? And this whole thing is, so the sea urchin is completely covered with all these threads in every direction. And the question is the volume there of thread, you would think, is even more than the volume of thread covering the I'd have to calculate, but intuitively, I'd say that there's more thread there because remember, for every 3 threads, because diameter is, you need 3 times the circumference to get the diameter, pi, right? So 314.
Yeah, but this is very simple, pi. If you have a thread going to the center, straight through, that's diameter, and you have the other one going around.
Yeah. So there's 3
times around one.
So there's 3 times more. So there's 3 times more. What is it?
Going around.
Around, but it's less. It's really it's 1.6 whatever. Because 1.57 times, because you're only taking half. The circumference. So half the circumference versus
the
diameter.
Assuming
1.57.
Assuming one thread goes perfectly around, which you say it doesn't. You say it snakes around, and God knows where that one goes.
Yeah.
And assuming the one in the center goes straight through, which it might not.
Okay, so we'll round it off at 1.6.
But it's a matter of assumptions. Where assuming the one in the center goes straight through, 180 degrees. No curving, no turning corners, just go straight through the center and straight out the back of it.
Yeah.
And the one that goes around, the magnetic one,
that
one goes exactly around, takes no detours to 180 degrees on the other side, and in a way, combines with the same thread that it went.
Maybe. We don't even know.
These are a lot of assumptions.
That's
what I'm saying.
Yeah.
That's how you kind of have to rationalize this. Because another thing we don't know is if there is a knot, so to speak, inside the proton, inside the center, if if the thread that goes inside kind of does a few loops and then goes out,
or at least even turns the corner,
or if it even turns the corner. There's three assumptions there. Does it go straight through? Does it turn? Because it can turn a 180 and go right back the way it came, kind of thing.
Yeah, yeah.
Or does it make a knot?
In which case, we can call that one a neutron.
Why is that a neutron?
Because here you have one thread coming in, that same one goes out, okay, and it winds itself.
Oh, that's weird.
I mean, there's a lot of assumptions here we can make.
An assumption there could be you can have an atom that is comprised of a bunch of ropes, in the sense that the rope goes in, and that thread, the thread goes in, and that same thread goes out to combine with itself, and it's the same on on every rope. So every rope just kind of goes in, breaks up, but comes back to itself.
That's why I'm saying it's not so far-fetched.
You get a lot of assumptions.
That's why I'm saying it's not so far-fetched to say that a neutron converts into an atom and vice versa. There are different scenarios, and we can't go crazy on this. Believe me, it's one of those things you got to take one assumption at a time, discuss. Long time with someone who doesn't agree with you, and that's where you exchange ideas and say,
forget agree with you. This is something you have to figure out even in your own head.
Yeah, you got to try to figure out how Mother Nature is doing her little magic
and it's a matter of assumptions. Okay, does this assumption give me a better result than this assumption?
Yeah.
It's just a what is it? Process of elimination, where you go, okay, this one is possible, but it gives me more headaches, or seems weirder, or has some Occam's razor issue going on.
You go with Occam's razor.
Okay, this is the most probable. At least belief-wise, I believe this is the most probable. There, you're up to choosing.
And then you go into religion, say this is the one I believe in.
I had another question about...
let me move on here, because we have questions from these other fellows. I just want to mention here once again, where is it? Here we have Monk's picture, okay? And it's a little kindergartenish, but essentially I think he's showing the same thing that I showed, unless he can correct me. He's showing the neutron there, which is just a cross-section, a crossroads of ropes, I guess. And deuteron, I guess he's referring to the deuterium. And again, I guess you got to make a better picture, Monk, if you're listening to me. It's not quite clear exactly what you're, drawing there. A better picture I get from Dan. This is his neutron, and I kind of like that. He spent, a little more time, or maybe he's a better artist or whatever. And I like that bottom right one, okay, where the neutron superimposes on a proton. I think that's what he was trying to portray. I kind of like that. Here's his second picture, which is shows even a better image, where he says, look, here what we have is the like a cross section of the atom and what they're doing in there. And I guess he's referring to, again, tritium there. So it's it's the hydrogen atom with two neutrons. And again, he's putting the neutrons in there, okay, and they're superimposing on the proton, which is just a convergence of threads. So I thought that was a pretty neat picture. We have Martin, and Martin came up with something which I need to clarify today. He disagreed with my model. He says he's got a better model. Okay, let's look at it. He talks about mating. Okay.
No, I remember mating.
Yeah, a little sex there, and that's not bad in our business. We need sex. Okay. And okay, so here it's not very clear, but he's got a better thing here. He put on in the forum, and this is his mating. And if you look at it carefully, you'll see that what he is proposing, that there's two parallel ropes. Okay.
Whoa.
And one of the ropes is releasing one of its threads, and it's combining with the thread of another one. Okay?
This is getting complicated.
Yeah. So there are different ideas. That's why we got to listen to everybody here, and you can see that the other one, one thread from one rope combines with a thread of this rope, and vice versa to the other pair. And so we end up with, I suppose we've got two different ropes now.
Yeah, but they switched
Oh,
threads.
they switched. Yeah, they switched. So he calls this mating. Okay, and that's good input there. Here's his explanation. Let
Oh,
me
no,
get.
they didn't switch.
They didn't. No, it's the red still.
The top red still combines.
Oh, it still
the top
combines.
red,
Okay,
still...
but what he's saying is, I guess that those loose threads that you see there going all the way to the bottom, I guess that's going to become the neutron, the atom. I'm not sure. That's let's see what he explains it here. He says, look, what is mating? At the shell, at the E shell, one rope splits. Okay, fine. In other words, you can say it forks out, but he's saying it splits. In other words, it does fork out, but he's going to do something with two of the threads from two different ropes. But the thread that should pass straight through would need to mate in order to form a new rope within the shell. Mm-hmm. And that's, I guess, the neutron, because that's a convergence of rope. That's what a neutron is? So I think he's referring to that. Any rope within the E shell must come from mating of two different atoms. Okay? Okay, so he's saying that the ropes inside the shell, right? The electron shell come from two different atoms. So here we're having good brainstorming. You don't have to agree, but you have to concede that people are using their brains to try to figure out how this really is structured.
It's definitely good to keep in mind the flexibility of, or the possibilities of patterns that these ropes and threads can make.
Yeah.
Or it's not always just the simple EM rope that you kind of show, because there's also the other one you never talk about is amplitude, which kind of shows here with the ropes, the how what do you call it, wide or thick?
How tall, you can say how tall or how far apart.
Because you always just draw it like the two ends there.
Yeah,
but there's a lot of patterns. You got one swishing around. You got these with big amplitudes.
And it's important, you know, what you just said, because amplitude has to do with intensity. So when light has a higher amplitude, it has a higher intensity, or at least that's the official version. Always keep in mind that, you know, that's the interpretation. But this has been around for at least 100 years. And so you could say, well, you know, they've done a lot of experiments out there. They did a lot of testing, a lot of measuring. This is what they came up with. They say higher amplitude leads to, you know, brighter light, or, you know, shinier light, more intense light. And so, you know, under the rope model, we can still explain it. We can say, okay, you know, the architecture of the rope does have amplitude built into it. Okay, so we have no problem with amplitude. But then here you have Martin's mating, and it's interesting how he pictured this, besides it being a very good picture, the one on the top, that with the explanation, you know, gives us a good view of, you know, how this thing could be really structured in there. Let me continue with his description here. Any rope within the shell must come from mating of two different atoms. Okay, the rope length within is equal to the atom diameter, a distance. Okay. Okay, fine.
Wait, rope length?
Yeah, the rope length.
But not thread length.
No, right. But essentially, he's saying the rope length is like the thread length. It's just the diameter of the atom. Okay, fine. Or you can even call it the radius, because again, if it turns the corner at the center for whatever reason, which is another possibility, then we would be talking about the radius, which is still more or less in the ballpark. Okay, the left behind thread, the one that stays behind, has no way of mating with its original mate until that buddy has left his newly found gay thread. Okay, the homos from two different atoms, rope within the E shell. So to keep its mental health, it spins around, forming the shell. Okay, so now what he's saying is that we have a spinning of this loose thread, and that's what's going to make the electron shell. And that's another version, which is not so bad at all. I mean, what we're saying here is the following. You can either think of the electron, the magnetic thread, as undulating all around the electron shell, which is what Mr. de Broglie proposed. He said that he said it this way. This is his equation, and it says that the electron shell, or under the rope model, right? The magnetic thread goes all the way around in integral links. There's never half a link, and that's something to keep in mind there. And de Broglie's equation would work against what Martin is suggesting, that there's a single loop around, or that it's a perfectly smooth shell made of one magnetic thread that's just spinning around, and that those magnetic threads that are spinning around the atom form the shell. De Broglie's equation says, look, this thing undulates all around the cloud, right? This is the cloud model, or a precursor to the cloud model. The cloud model comes with Max Born a little later. But essentially what he's saying is, look, when I go around in a two-dimensional plane, the thread in our case, the electron.
But it's a snaking thread.
It's a snaking thread. It's not a smooth thread that just goes around like a circle. And if Martin's making is correct, at least for how the electron shell is built, then we do have a little bit of problem, because it violates de Broglie's equation. And again, we have to keep these things in mind to some degree, because if something has been measured, I guess, or they say, look, there's some kind of wave going around. The electron is really a wave that's stretched all around the perimeter of the atom. Then if it's a wave, well, then you have to think that it's the thread that's kind of undulating around and not smoothly all around. Okay, so just keep that in mind.
Yeah, I imagine like many snakes kind of snaking along the shell.
Yeah,
it's not that they're spinning, it's kind of like the slack goes in. Whatever slack there is in the universe goes into the shell in the form of a snaking thread among other snaking threads. It's like a ball of yarn of snaking threads. It's kind of like this, kind of like creepy, like vibrating.
The way I visualize it is that this thing goes around snaking around.
Is it in and out, or up and down, or along the surface?
You take the assumption that most fits your theory, okay?
Yeah, I guess so, right?
I mean, you can do it up, you can do it outwards, or you can do it, parallel to the surface.
Exactly.
Either way, but or even at angles from there. But this is the point. The point is that the way I visualize this thing, let's see if I have an image that might put this into right perspective. Let's see here. I'm going to try to find it real quick. Give me a second here. Give me 1 second. I think I've got the image that I want. Let's see. It's over here.
And vibrating is the wrong word.
Vibrating.
But it's kind of this faux vibrating. It's like a fake vibrating. Because it's not that it's kind of shaking. It's this snaking of zillions of single threads. They give it this vibrating, illusion.
Here it is. Look. Think of it as something more like this, like the donut, and think of this really as a ball, okay? But I'm putting a donut here so that you can see what the idea. Maybe the outside of an electron looks something like that.
No, it's weirder than that.
Well, no, but I mean that gives you a little. In other words, I think this thing is the outer skin of an atom. In other words, the electron shell, the balloon, has that kind of motion on the outside. Maybe if we had God's eyes, that's what we would see, or something similar to this. Okay, some weird twisting in situ. Okay, something like this. And maybe what we're looking at there. Now think of it this way. Think of that as a single thread there. Just think of that as a single thread going around. We've just made it big. Okay, so that's one thread going around the electron shell, right?
That's a good question.
And maybe it just twirls on itself. each thread, and
so you're saying
every thread would
the
be like
threads
this.
are spinning
Like
on its own axis.
on its own axis, you know, and
True.
this is maybe what this is showing.
Wait, that's a
maybe
good
this is one
question.
thread.
That's a good question. Is the thread a circle, a cylinder in a way, or is it like a shoelace where it's like flattened?
I would think it's more like a cylinder. That's the way I imagine it. But again, and this would show that, yeah, that's the idea it would show. But if you think of this as just one thread, maybe the thread is doing something similar to this with some kind of motion like this. We have Martin Yarhold. He says, this is just two ropes. Imagine gay ropes from all atoms, okay? I'm just looking for an explanation to why an atom stays an atom mating. Okay, the only thing I'm saying, Martin, factor in, when you look at this, right, factor in de Broglie's equation. And de Broglie, Louis de Broglie, Frenchman, he received the Nobel Prize, I think, he came up with this in 1923. So a few years later, in those years, he probably got the Nobel Prize one of those years. And anyways, what he said is, look, the electron moves around. Again, he modeled this with particles, right? But he says it moves around as a wave, and that's how they brought the wave back into quantum. The wave was dying. With a photon, with Planck's constant, the wave was dying, and it was de Broglie who brought it back, saying, look, even electrons move as waves, and he thought of them as a little bead that moves, you know, in undulating pattern around the perimeter of the atom. And he says, you know, this little snake that's moving around, it comes in integral waves. In other words, the wavelength is always integral. You don't have half a wave, you don't half a link. You don't have a quarter of a link, you always have a full link. It's all integral all around. And that's what de Broglie's equation means or says, okay? And so keep that in mind, because if this thing is like I'm showing there, you know, somehow, I don't know, twisting on itself and it's undulating, maybe it's not completely straight for whatever reason, then you have to factor that in, what you're proposing of, you know, that maybe because I consider that as well, the fact that maybe the electron is a skip rope where, you know, the two ends are just twirling the magnetic thread around, and all these gazillions of magnetic threads twirling around form the shell, and in different directions, by the way, okay? So that's one possibility. But again, you know, and let me say one more thing, Martin, and keep this in mind. Imagine a ball of yarn. I don't have one here, unfortunately, but I'll probably bring it next time. And just imagine all those threads in different directions, all around the ball of yarn. You know, it's tied in every single direction possible, imaginable, right? And then, yes, it's not a smooth surface because, in a sense, you know, one's on top of the other. Maybe there are a couple layers of this also. And maybe that's where de Broglie gets his, you know, integral waves. So there's a lot to brainstorm here. We have to try to visualize what this thing might look like under the rope model. And I think you've done a good job with your two strands forming, you know, mating. You get 10 points for that one. Okay, it's one possibility, of course. Anyways, we'll see. Time's up, so we'll see you tomorrow, same time, same station. Keep brainstorming. And for those who are going to Buenos Aires, keep in mind, 10th of Saturday, the 10th of November, we have a conference down there. We're going to have a lot of fun. Those who miss it, well, all I can say, I'm sorry for you because you're going to miss it. We'll see you tomorrow, same time, same station. Bye-bye.